Let's talk about something wild. Engineering massive pipelines to survive deep under the sea.
We're going to break down the 5 key steps engineers take to make sure these things don't fail.
So what's the biggest threat down there? It's probably not what you're thinking. It's way more subtle.
It's not some giant sea monster or a collision. Nope, the real danger is just empty space, gaps.
They're called freespans, and they leave the pipe hanging, exposed to all sorts of dangerous vibrations.
So where does checking for these gaps fit into the whole design process? It's actually fascinating.
Well, it comes right at the end. It's one of the absolute last, most critical safety checks.
Engineers actually have a super strict checklist for every single one of these freespans. Let's walk through it.
First up, they do a quick and simple screening test. This weeds out the spans that are obviously okay.
And here's the fork in the road. If it passes, great. If not, things get a lot more serious.
Next up is a deep dive fatigue analysis. Can the pipe handle millions of tiny vibrations over decades?
And finally, every span has to pass what's called an ultimate limit state, or ULS check. The fatigue check is about those repeated stresses from currents. Think bending a paperclip. It eventually snaps.
The ULS check, though, is for that one massive event, like a 100-year storm. Will it buckle?
For fatigue analysis, engineers use this cool tool called an SN curve. It's all about trade-offs.
Basically, the higher the stress, the fewer times you can apply it. This lets them calculate total lifetime damage.
For the ULS check, they throw everything at it. Weight, vibrations, waves, even fishing gear to find max stress.
But, the real world is messy. The ocean's unpredictable. So how do they build in a safety net?
They do it with safety classes. You can see here, the higher the risk, the less damage is allowed.
So for a high safety class pipeline, it has to be a whopping 4 times stronger than the bare minimum.
These safety margins get applied to everything. Stress, frequencies, you name it. It makes the design super robust.
So deep down, there's this incredible dance of physics and safety checks going on. Makes you wonder, right?